Good day everyone, I am Daniel J.P. Saldaña from the group of JSON method. And today, we will discuss the naive string matching algorithm, its human simulations, code tracing, and assessment conducted in its results. The naive string matching algorithm is a specific type of brute force algorithm and is considered the simplest method for string processing. It has no single creator or precise date of origin, as it is developed naturally in the early years of computer science. The algorithm is called naive because it checks for a pattern match at every position in the text without using information from previous checks, which prevents it from making optimized decisions. This algorithm searches for a pattern within a given text by shifting from left to right, starting at index 0, and continues to execute until the last iteration. The number of iterations is determined by n minus m plus 1, where n represents the length of the text and m represents the length of the pattern. And this algorithm does not use pre-processing and returns a result immediately whenever the pattern matches the text completely in a particular iteration. It has a best case time complexity of O of n, where this algorithm is fast when there is a mismatch immediately at the very first position of the pattern in every shift, or the pattern has only a length of 1. On the other hand, this algorithm has a worst case time complexity of O of n times m, and this means this algorithm is slow because it checks all of the positions of the pattern being searched in every index or positions of the text. Or in other words, many of the initial letters match at the beginning of the search, but later on, it was found out that there is no complete match between the pattern in the text and every iteration, and this increases the time of searching.
In this example, the text is CCCCCX and the pattern is CS. The text has a length of 6 and the pattern has a length of 2. The number of iterations are determined by n minus m plus 1. N represents the length of text and m represents the length of pattern. So that is 6 minus 2 is equals to 4. Then 4 plus 1 is equals to 5. So there are 5 iterations for this example. In the first iteration, the alignment of the pattern to the text starts with the index 0 of the text by placing the first letter of the pattern, which is C, to the index 0, and placing S to the index 1. Now, the C and the pattern match to the index 0, which is also C. Then, let us move to the next position. S from the pattern does not match with the index 1 of the text, which is C. So, this means there is mismatch in the first iteration. So we now move to the second iteration. Here is the path of the first iteration. For the second iteration, the alignment of the pattern to the text starts with the index 1 of the text by placing the first letter of the pattern, which is C, to the index 1, and placing S to the index 2. Now, the C and the pattern match to the index 1, which is also C. Then, let us move to the next position. S from the pattern does not match with the index 2 of the text, which is C. So this means there is mismatch in the second iteration. So we now move to the third iteration. Here is the path of the second iteration. For the third iteration, the alignment of the pattern to the text start with the index 2 of the text by placing the first letter of the pattern, which is C, to the index 2 and placing S to the index 3. Now, C and the pattern match to the index 2, which is also C. Then, let us move to the next position. S from the pattern does not match with the index 3 of the text, which is C. So this means there is mismatch in the third iteration. So we now move to the fourth iteration. Here is the pass of the third iteration. For the fourth iteration, the alignment of the pattern to the text start with the index 3 of the text by placing the first letter of the pattern, which is C, to the index 3 and placing S to the index 4. Now, the C and the pattern match to the index 3, which is also C. Then, let us move to the next position. S from the pattern does not match with the index 4 of the text, which is C. So this means there is mismatch in the fourth iteration. So we now move to the fifth iteration. Here is the pass of the fourth iteration. For the fifth or last iteration, the alignment of the pattern of the text start with the index 4 of the text by placing the first letter of the pattern, which is C, to the index 4 and placing S to the index 5. Now, the C and the pattern match to the index 4, which is also C. Then, let us move to the next position. S from the pattern does not match with the index 5 of the text, which is X. So this means there is mismatch in the fifth iteration. Here is the pass of the fifth iteration. And now, the algorithm will return no complete match found between the text and pattern. Now, we can conclude that this example is a worst-case time complexity because every first position of the pattern match with the text in every position, but the second position is mismatched in every iteration, which is forced the algorithm to check in all positions, and that resulted to the longer execution time for the algorithm.
In this example, the text is ethics and the pattern is E. The text has a length of 6 and the pattern has a length of 1. And there are 6 iterations for this example. In the first iteration, the pattern starts checking in the index 0. Now, the pattern E match with the index 0 of the text, which is also E. So the algorithm returns a complete match is found at index 0. Now, the first iteration is finished. And here is the pass of the first iteration. And now, we move to the next iteration. In the second iteration, the pattern now moves to index 1 of the text. Now, pattern E does not match with the index 1, which is T. So, this is a mismatch. And now, the second iteration is finished. And here is the pass for the second iteration. And now, we move to the next iteration. In the third iteration, the pattern now moves to index 2 of the text. Now, the pattern E does not match with the index 2, which is H. So, this is a mismatch. And now, the third iteration is finished. And here is the pass for the third iteration. And now, we move to the next iteration. In the fourth iteration, the pattern now moves to index 3 of the text. Now, pattern E does not match with the index 3, which is I. So this is a mismatch. And now, the fourth iteration is finished. And here is the pass for the fourth iteration. And now, we move to the next iteration. In the fifth iteration, the pattern now moves to index 4 of the text. Now, pattern E does not match with the index 4, which is C. So this is a mismatch. And now, the fifth iteration is finished. And here is the pass for the fifth iteration. And now, we move to the last or the sixth iteration. In the sixth iteration, the pattern now moves to index 5 of the text. Now, pattern E does not match with the index 5, which is S. So, this is a mismatch. And now, the sixth iteration is finished. And here is the pass for the sixth iteration. Now, we can conclude that this example has a best case time complexity of O of n because the pattern has only a length of 1. And this results to a shorter execution time because it only requires one comparison per iteration. In the third example, the text is I, heart symbol, DNFC, and the pattern is SC. The number of iterations for this example is 5. Now, let us start the execution. We can conclude that this example has a time complexity of O of n because there is a mismatch at the first positions from the first to fourth iterations. But we cannot call this a strict best case since the last iteration checks the whole positions of the pattern, which resulted to a complete match with the text. Because the definition of the best case complexity of this algorithm is there should be an immediate mismatch at the first position in every iteration, or the length of the pattern is only 1. So, theoretically, we can consider this example as O of n since it grows linearly with n.
I'll explain a simple Java program that searches for a specific pattern in a given text. We will take an input text and pattern from the user, and the program will tell us if and where the patterns in the text. So first, it is important to us to import Java util. The method declaration takes two arguments, which is the text and the pattern. We store the length of the text and the pattern in textlen, or simply as text length, and the pattern is stored in the path length or the pattern length. So the outer loop we use for loop is to slide the pattern along the text. This is our outer loop. This run from the 0 index to the text minus path length so that we don't go out of bounds where the pattern is suitably fit. So in the outer loop, at each position, we assume the pattern matches. So we initialize the boolean variable to true. We only assume that the first index of each inputted text and pattern is true, but we'll change it for later. So here in the inner loop, this is our inner loop. There is another loop that checks each character of the pattern. If the outer loop checks for the inputted text, then the second loop will check each character of the pattern character. So if any of those index does not match, then we set is found to false. So if index 0 is not equal or match to the index 0 of the pattern text, then we assign the is found into false and then break the inner loop and goes back to the outer loop. So this is the core comparison of the string matching. This is where the comparison function works. It compares each character by each character. So next, if the pattern is found inside the text, then the is found remains true. After the inner loop, it means the pattern matches the text starting at index I. So we print the index where it was found. So if it is found, the pattern was found inside the inputted text, then the starting index of the found character, then that will be the index where it will be found. After the loop, if any character is still false, any of those character of the pattern does not exist in inputted text, then this block of code will be executed. So every iteration of the found any is still false, then this code will be executed saying that the pattern does not exist. So here in the main code, this is where this is where the user inputted those texts in order for our algorithm to work. So for example, let's say my text is DNSC and the pattern S and C. The program will be outputted that pattern found at index 2. So why at index 2? It's because the S is in the position of index 2. Since we're starting at the number 1, then N will be 1 and S will be 2. That's why that the pattern was found at index 2. If any of these pattern does not exist in the inputted text, for example, we have the NSU and we're looking for the the letter S and C, then the pattern does not exist. It's because we are looking for the letter S and followed by C, but the inputted text doesn't have that kind of pattern. So in short, this program demonstrates a simple string matching algorithm that comparing each substring of the text with the pattern. So it is easy to understand and implement. For smaller index input, we can say that the naive string algorithm works really fine.
An algorithm assessment conducted by the two computer scientists, namely Lovis and Bod, where they determine the fastest algorithm in exact string pattern matching using medical language. 5 algorithms are compared, namely naive string matching algorithm, the North-Morris-Pratt algorithm, the Karp-Rabin algorithm, the Boyer-Moore-Horspool algorithm, and BMH2 or a variant of a Boyer-Moore-Horspool algorithm. The assessment used Object Pascal using Delphi version 4.0.3. The test used 3 patterns such as dyspraxia, polychondritis, and superficial injuries of wrist and hand. For the word dyspraxia, the result shows that the Karp-Rabin algorithm is the slowest, which has 296.63 milliseconds, then followed by the North-Morris-Pratt algorithm, which has 229.26 milliseconds, then followed by naive string matching algorithm, which has 131.93 milliseconds, then followed by Boyer-Moore-Horspool algorithm, which has 77.71 milliseconds, and the BMH2 is the fastest, which has 77.30 milliseconds. The naive string matching algorithm shows relatively low variability across runs, indicating consistent performance for short patterns. Throughput analysis confirms that the naive string matching algorithm is acceptable for small patterns, but the number of character comparisons grows with longer patterns. In the word polychondritis, the result shows that the Karp-Rabin algorithm is the slowest, which has 462.21 milliseconds, and followed by the North-Morris-Pratt algorithm, which has 365.95 milliseconds, then followed by the naive string matching algorithm, which has 199.25 milliseconds, and followed by BMH2, which has 108.71 milliseconds. And the Boyer-Moore-Horspool algorithm is the fastest, which has 108.70 milliseconds. Memory usage for naive string matching algorithm was minimal compared to KMP and BMH variants, and requiring only a few bytes of extra space. The last word is superficial injuries of wrist and hand. The result shows that the Karp-Rabin algorithm is still the slowest, which has 632.8 milliseconds, then followed by the North-Morris-Pratt algorithm, which has 468.25 milliseconds, then followed by the naive string matching algorithm, which has 273.58 milliseconds, and followed by Boyer-Moore-Horspool algorithm, which has 108.81 milliseconds, and the fastest is the BMH2 algorithm, which has 100.70 milliseconds. The overall results of the algorithm assessment indicate that the naive string matching algorithm is efficient for short pattern searches, but less effective for longer patterns. This confirms that while the naive string matching algorithm remains competitive for short patterns in medical texts, algorithms such as BMH and BMH2 algorithms deliver considerably higher throughput for long or complex patterns.